So the first technique for measuring performance I wanted to talk about is using something called CUDA events to measure performance. Probably people in this class have thought about getting the wall time, launching a kernel, doing CUDA device synchronize, and then getting the wall time again to measure events, or to measure performance, but there's sort of a built-in and lower overhead way to measure times in CUDA that's a little more flexible with respect to measuring the performance of asynchronous operations as well. So this isn't directly related to profiling, but it's relevant. So we're going to need to understand something called a stream, which is sort of a queue of sequential CUDA events, and so each one is executed after the prior one finishes, and you're able to insert things into these queues, such as kernel launches and memory copies. Your program can use any number of these streams, and each of these streams is associated with a particular device. There's some exceptions to that. You may say, well, I've never used a stream before in my CUDA code, and the answer is you do. If you don't explicitly use a stream, you use something called the default stream. This stream actually has some special semantics as well, which I'm not going to get into. You can look them up if you're curious. Then there's something called an event, which basically records the state of a stream. So at the time the event is executed, it will basically capture what's going on in the stream for you to reference later. But generally, to overlap operations, you want to use different streams for these operations. You want to avoid using pageable memory, so you want to use pin memory on the host, and you want to use the async CUDA runtime functions. So I think this will all make a little more sense with an example. So let's just time a particular set of operations. So on the left-hand side, basically there's a bunch of code to create and initialize these streams. But the real takeaway is what you're going to do is before and after the things you want to measure, you're going to call CUDA event record to insert different events into the stream. So in this example, we insert the start event before the CUDA memcopy call. And then after the kernel, we do CUDA event record on the stop event. So these basically inserts these events into the stream, and when the stream proceeds enough to reach those events, it will record them. And then you can ask CUDA how much time elapsed between those two events once the second event has happened. So in this case, we would be measuring how much time elapses between the start of the memcopy and the end of the kernel execution. So in order to ensure that the second event, the stop event, has happened, we have to call CUDA event synchronize. So that is just like CUDA device synchronize, except instead of waiting for the device to be finished executing work, it waits for the event to be finished. And then we can use this CUDA event elapsed time call to get the number of milliseconds as a float that elapsed between the start and stop of this event. So this allows you to easily measure the time between the time that certain CUDA operations take, any number of operations that are not executing synchronously with the host. So this is sort of the most flexible and most accurate way generally to measure the performance of specific events. This is actually the technique that we use to print these results, so if you go look at that code, you'll see that. But basically, the other thing I wanted to highlight is that typically the first time you execute some GPU code, the performance will be slower. This may have to do with the GPU clocking up, or there being cache misses, or other things in the system needing to be initialized the first time they're used. So typically what we'll do is some number of warm-up runs that we don't contribute towards our performance measurement, and then some number of actual times that do contribute to the performance measurement. So if you look at the output of your RAI run, you'll see a bunch of lines that look like this, and I just annotated the ones that we actually count with a star. So when I run those three different matrix multiplications I just talked about, the basic one, the tiled one, and the joint one, these are the numbers I get. So you can see that we get some small amount of speed up from using shared memory. Based on what you were led to believe in lecture, this may seem like a disappointing speed up. Maybe you were hoping for much more. The profiling can help us understand why that is. And you can see this joint matrix multiplication is really much faster. And so hopefully by the end of the lecture, if we don't understand why this is true, you'll be well equipped to figure out why it's true if you're curious enough to do it.